So the simplest type of rootkits, and the ones which might be, for example, used to hide malware from a user rather than anti-malware application, are user-mode rootkits. And the user-mode rootkits would attack only the user-mode part of the operating system, and specifically, they will attack applications themselves or NTDLL layer. So, as you might know, or as you can see from this diagram, every application or every process in Windows operating system will have its own virtual memory. It means each of them would have its own copy of kernel 32 DLL or NTDLL or pretty much any other DLL loaded. So here I depict Explorer, Task Manager, and a malware process. It's very simplified picture, so that each process has the main image, for example, explorer.exe or taskmanager.exe, and they also have kernel 32 DLL and NTDLL loaded. Of course, there are much more DLLs loaded into this process, but for our example, it's enough, good enough simplification. And we have malware process with a malicious image loaded in it as well. So if malware wants to deploy the rootkit, what it would do in case of user mode rootkit, it would inject its own DLL into target processes. It can deploy it to all the processes, but it also can deploy it only to specific ones instead of all of them. So it would inject its own DLL. It can also be a shellcode, but shellcode is a little bit more advanced. Most of the time between 2005 and 2010, that would be just a DLL. And so what this DLL would do, it would need to hijack a benign API calls, right? So when the application needs something, it performs an API call. An API call is implemented in one of these DLLs, benign DLLs or other DLLs, right? But for rootkit purposes, we would focus on those DLLs. And so the way it usually looks like, it's a call instruction, but not direct call. It's a call instruction through the address table, which called import address table, which has multiple records of where APIs are, right? And so malware has multiple opportunities. Of course, what malware could do is go and analyze explorer.exe and find every single call and try to patch the code of the explorer.exe. That, however, is very unreliable, can cause a lot of issues, and can be very unstable. So instead, what malware can do, it could find interesting records in import table, for example, create file or open registry key APIs, and override those addresses with its own addresses, which would point to malware itself. In this case, this address gets hijacked, and instead of calling the kernel 32 in this case, the application would first call into malicious library, then malicious library would call the actual API. The API will return results to malicious library can filter results, and then return filtered results to the Explorer.exe. For example, this way, when the Explorer.exe lists all the files in the folder, malware can remove malicious files from that list, and then user would not see the actual file inside the folder. However, this method doesn't really work well when the process dynamically gets the API addresses, for example, through getProc address. That means malware would need to intercept getProc address to intercept everything the getProc address receives, and then that becomes messy very quickly because there is no clear import table to hook. So what instead malware can do, it can actually modify code inside the DLLs. And since every process has its own virtual copy of it, it pretty much can only hook for specific process. It means when the API is called, the benign file benign process would still call API as usual, but then API would actually go into the patch, and that patch would redirect the API into extra malicious code, or it can redirect it to original shellcode injected. The shellcode or DLL will filter the result of API and then return back and execute the rest of the code, and then it would actually come back to benign file. Let me give you a more specific example of Usermode rootkit. Imagine that the whole slide here is the Usermode memory of one process. In this case, is Explorer.exe running, and the whole slide on the left side is the Usermode memory, and on the right side you have a kernel mode memory, right? And what I will show you is how normal API is getting called when it's called by the application, what actually happens under the hood. So if the application, in our case is Explorer.exe, is calling, for example, FindFirstFile to show you all the files in the current directory, right? You as a user browsing through your directories, you want to see if certain directory contains anything suspicious. You click on that directory and it enumerates the file using FindFirstFile, FindNextFile, and just enumerates through the list. And so the first it will call this FindFirstFile, and then here's Explorer I'm talking about, and it will call this call, right, inside the memory. So if you imagine that that's this mzp file, that's our memory of our main image. We have a call, and this call is going through import address table. This particular instruction would say call the function which address is located on this 404010 memory region, and that's the memory region inside the import table. And that memory region points to the first file implementation in kernel 32. When the call happens, the memory gets looked up, and that the value from the memory is used to actually call the function. And in this particular case, that's the address FindFirstFile function. And this function starts with it's a 32-bit process, so it starts from a standard stack frame, and then the code gets executed, and at some point it actually calls ntdll. And it does it the same way. It lookups its own import table, it finds the address of nt query directory file, which is another function, and that function is inside ntdll. ntdll implements a center. That's actually instruction for 32-bit processes, which actually would jump into the kernel mode, and after that kernel mode code would execute actual implementation of nt query directory file, then it returns the list. Kernel 32 would parse the list and return the pointer to that list to Explorer.exe. So there's a whole cascade of different API functions. Because there is a whole cascade, there's actually multiple places where rootkit can intervene. Specifically, let's say the rootkit gets loaded, and just for simplicity, I'll put the rootkit, Usermode rootkit code here. And let's say it's another mzp file, which is malicious rootkit DLL. And so what this DLL can do, first of all, the easiest way for this DLL is to override the value inside import address table. In this case, when this call instruction is going to look up the value, instead of the value inside kernel 32, it would be hijacked and the code will jump into the malicious DLL. This malicious DLL can implement the rootkit functionality. For example, in this specific case, it cannot filter a result yet. So what it will do, it will actually call the original FindFirstFile. When the FindFirstFile will call ntdll and will go to kernel mode, then it's going to come back and it's going to return the results back into our malicious DLL, and then malicious DLL would filter a list of the files and it exclude malicious file out of that list. So that would be one place to intervene for malicious DLL, that's to patch import table. However, if the benign application, instead of calling a function through the import table will actually dynamically resolve the function through getProcAddress, then the getProcAddress will directly return the value of the FindFirstFile. In this case, the rootkit would be bypassed and would not really work. To solve this problem, rootkits would usually override these first bytes of the actual function with a jump into malicious memory. So when the FindFirstFile will be called, instead of the first two instructions, push EBP, move EBP, ESP, which is very standard stack frame, it would execute the jump to a malicious DLL. The malicious DLL then can, for example, substitute the return address to its own and then continue execution of the kernel 32 DLL. And then when kernel 32 DLL will return, instead of returning to the original benign, the Explorer XZ, it would return to malicious DLL first, and then malicious DLL will filter the results again. So that would be another way to do it. Of course, some applications, maybe not Explorer XZ, but for example, antivirus applications can, instead of calling FindFirstFile, directly call NT-query directory file, right? And try to kind of bypass potentially a patched kernel 32 DLL. So what, of course, rootkit can do as well is to patch NTDLL with the jump as well. And then if kernel, for example, kernel 32 DLL calls NTDLL, it will call it, but then again, execution is going to be hijacked, return to rootkit DLL, the results going to be filtered, and so on. So you see that in the user mode, it actually has many different opportunities where to hijack the execution flow to modify it and hide the results of legitimate Windows API and syscalls by filtering results at the end. And this is just one example. Of course, FindFirstFile and NT-query directory file is not only APIs and NT calls which can be hijacked and filtered. Pretty much rootkit can hijack any API the similar way. So there are multiple different ways, all depends on sophistication of the rootkit, but that's pretty much how user mode rootkits would work. Again, they are working per process basis, meaning each process has to have a user mode rootkit injected into it. They have multiple locations where they can hijack the execution, starting from import table of the main image, going to the kernel 32 DLL and TDLL, either stealing a first few bytes of the specific function or being more sophisticated and stealing code in the middle of the function, depending again how complex the rootkit code is.